Hello, everyone. This is Professor Ali Tarrad, and welcome again to my channel, Thermal Engineering Concept and the Principle. And in this episode, I will talk about heat conduction in other physical objects, such as cylindrical and spherical objects. And let us start. As we talked in the previous episode for heat conduction in the plane wall, I have prepared another part for the heat conduction in conduction of what we call it in this cylindrical and spherical coordinates, and that um, has many application in technology, and I will pass through some of them during the uh, explanation of heat conduction in these coordinates in this episode. In this part of the video, we are talking about heat conduction in a cylindrical object. Uh, as you see here is a pipe with its own dimensions, and it is exposed to airflow on the outside in effect that for convection part. But let us focus on the tube itself, how heat can be transferred through its body and its thickness in the radial direction. So we have the inside temperature is Ti, and we have the outside temperature, uh, which is less than the inside temperature. So we will expect heat to be transferred in the direction from inside to outside. And the general form is Q equal delta T divided by R thermal. And the thermal resistance for the cylindrical object is defined as natural logarithm of d naught by di divided by 2 pi k L, and can be represented in a form of analogy to the electrical circuit, as we did that when we talked about heat conduction in the plane wall, and the overall temperature difference is equal to T1 minus T2. So this is how the process can occur, that heat is transferred in a perpendicular direction to the surface area of the tube. The practical application of heat conduction in pipes is the case where we have a composite cylinder. For example, this tube is insulated by an insulation material to minimize heat loss or heat gain between the fluid inside that tube and the ambient. So now we have two thermal resistances which are connected in series with an overall temperature difference between the inside and the outside is equal to T1 minus T3. As we studied before, that the thermal resistance for two layers can be calculated in the form of the first layer, which is for the tube itself, and the second part it could be for the insulation material. And that system is bounded by a total temperature difference between the inside and the outside temperature of the surface of the insulating material, which is delta T equal to T1 minus T3. In that sense, we have Q equal to delta T overall divided by the total thermal resistance, which are connected in series. And similarly, in the same way as we studied in the plane wall, that the heat transfer, which is transferred from the inside to the outside, should be the same for each layer. And that will help to give you the what we call it, the temperature distribution inside the the interface between these layers, as we studied in the same way as the plane wall. But we have to focus here that the surface area is different, changing as you go in the direction of increasing R, then the surface area is changing as well. And in that context, we may talk about the spherical object. For example, we have here a sphere with temperature difference T1, which is greater than T2. And uh, because of that, we will get a heat flow from inside to outside. And Q again is the same as we studied before. That is the total temperature difference divided by R thermal. And R thermal for the sphere is equal to 1 over Ri minus 1 over R naught. The total uh, value divided by 4 pi k. And again, we can represent it in the form of uh, an electrical resistance, as we studied before. And this form, as the animated part, shows that heat transfer is in the direction between T1 and T2. And the R thermal is expressed in terms of the radii, thermal conductivity of the materials. Now, let us focus on the composite spherical geometry. In this figure, we have a sphere with a diameter of D1 and the external diameter D2 is covered with another layer such as insulation with the specified thickness to compose an external diameter D3. Again, we have the uh, summation of thermal resistances in series, which composes of two. Uh, the first layer gives R thermal 1, and the second one uh, gives R thermal 2. And if we substitute R thermal, then we will get the one shown in this equation and can be replaced in a circuit with thermal resistances, and the Q represents the current which passes through system. And again, we may the constant heat that passes from one layer to another to calculate the temperature distribution. For example, T2, which is the interface between the external surface of the sphere and the inner surface of the insulation material, the red one, is expressed as T1 minus Q times R thermal 1, which can be replaced by 1 over R1 minus 1 over R2 divided by 4K1. Similarly, we may get T3. And if we substitute the values of the thermal resistance and T2, then we will get T3 as shown in the final expression of this slide. We have mentioned the thermal insulation in the previous episode for the plane wall. Similarly, we have some insulations which are used for any piping system to reduce or minimize the heat losses or heat gain from the fluids that are passing inside these tubes. For example, here is how the uh, insulation material could be prepared. For the first one on the left hand side, we have fittings and pipes. On the right hand side, we have another photo for these insulation materials to reduce heat losses or heat gain. And here we have also the first one at the bottom shows the insulation of piping from the steam turbine, and the right hand side shows an insulation for pipes in heating, ventilation, and air conditioning. And whatever the fluid that passes through these piping systems, whether it was hot water, steam, refrigerant, or even chilled water for cooling purposes, it should be insulated as well. Here we have a short video which shows a piping system for an cooling or heating systems, heating, ventilation, and air conditioning systems. And these pipes should be insulated to, um, as we said, minimize heat losses or heat gain to the fluids. And these pipes, as you can see here, are well insulated by an insulation material, whether it was steam or hot water. And again, it's a sort of safety for the people who are passing by these tubes or piping systems, in addition to prevent heat loss or heat gain. Here, let us take an application example from industrial side that where a steel pipe, 2 inches, conveys steam for the purpose of heating some equipment or utilities, and it has 30-meter long with condition that is 160 Celsius inside and 50 Celsius outside. And this pipe is insulated with a glass wool on the exterior to reduce heat losses to the atmosphere. As shown in this figure, we have the dimensions which are required to solve this equation. It is just to calculate the amount of heat loss to the atmosphere. Once you know the thermal conductivities of these materials and the dimensions, then it will be easy to calculate it. So it can be represented in two thermal resistances in series, and we have T1 is greater than T3, then the heat transfer will be in the direction from T1 to T3, and the Q delta T over all divided by the summation of resistances. We have T160 Celsius and T350 Celsius. which represent the outside surface of the glass wall. Then substitute these values for D2 and D3. Then you will get a general form which represents delta T overall divided by the summation of resistances, delta T overall 160 minus 50, divided by the summation of the resistances for the first uh, layer of tube, which is the material of the tube, corresponds to 0.461 times 10 to minus 4. And the second one is for the insulation, which corresponds to 0.1486. Then we will get a total heat loss of 740.26 watt. That amount of heat will dispatch to the atmosphere through the tube wall and the insulation material. And now let us consider another example for spherical object, a vessel, and it is considered as a spherical object with the outside diameter 22 centimeter and the inner is 19 centimeter with thermal conductivity of 1.0 watt per meter Kelvin. This is used to um, keep fluid, and we have the temperatures on the inside vessel wall and outside, where 20 and 25 is the outside value. Um, and In this case, we have the outside temperature is greater than the inside temperature. So that will give you an impression that the heat is transferred from outside to inside, which is, we call it heat gain by the fluid inside that vessel. We have here again all the dimensions, the vessel, the green one, and the insulation is the brown color one. And again, we can represent it by sort of thermal resistances in series. And then we may use the general form, which we have given just a few slides before. The inside dimension are 195 millimeter, out and are 210 millimeter, are 335.4. We have the thermal conductivities of these materials. Then we will get the total thermal resistance to be 6.8997 times 10 to minus 3 degrees Celsius divided by watt. And we may calculate the heat gain to be overall temperature divided by the resistances, summation of these two resistances in series. Then we will get 724.67 watt, which this amount of heat is gained by the uh, fluid which is kept inside the vessel. So now we approach the final part of this video. As a closure, we passed through cylindrical and spherical geometries and how heat is conducted through these objects in one-dimensional form, and single and multi-layers in the cylindrical and the spherical objects were studied. Uh, Steady state conditions were considered, that is, there is no energy accumulation inside these objects. And I think we have some useful resources. You may find them. And thank you for watching this video. and I hope to see you next time. Bye bye. So, I think we should mention that there is something related to this video, which will be passed on the next episode. So maybe the heat conduction with heat generation in these geometries will be considered as well in the future episodes. Have a nice time. Bye bye.